Here in Chapter 1, we still haven't learned how to solve any differential equations yet. But in Section 1.3, we're going to be able to possibly get a rough graphical representation of the solution to a differential equation using direction fields. So if you remember from Calculus 1, one of the basic applications for derivative is tangent slope. So dy dx equals tangent slope. So if we have a differential equation in the form dy dx equals f of x, or f of xy, potentially, we could have x's and y's there on the right-hand side, we could use that information to find some tangent slopes on our solution function. And we can find them just by picking some points on our graph. Now, these are just going to give us tangent slopes, so we know a tangent slope is only good at that exact point. So we can't draw those tangent slopes very large. They've got to be really, really small. So when we do this, these direction fields are just going to be graphs with lots and lots of little lines on them. If you remember from the last couple sections as well, we also could potentially have some arbitrary constants in our solution, and a lot of times these arbitrary constants are just a plus c at the end of your answer, which just shift your graph up and down. So without having any additional information about our solution function, phi of x, we don't necessarily know its exact position in the plane, but we can at least get a rough idea of its shape. If we were also given a specific point on phi of x, then we could possibly try to sketch the graph for phi of x, but we have no idea what the function notation, the function representation for this solution is. This is just purely graphical here in section 1.3. So let me give you an idea here of what we mean by direction fields. So if we have the differential equation dy dx equals, we'll just keep it simple for this first one, 2x. We are going to sketch the direction field. And these can get pretty large and elaborate. We're just going to keep it pretty small. There are an infinite number of points in the xy plane, and we obviously can't draw a tangent slope at every single one of them, so we're just going to pick a few points. If we want to get really serious about these direction fields, there is a strategy for picking particular points. We're just going to pick a few points and draw some little tangent slopes. So I'm just going to put a couple of values on here so we know where we're at. I'm just going to pick a point on the plane, and I am going to plug that point into my differential equation. And remember, dy dx means slope. So if I were to plug that point into the the right-hand side of my differential equation, it will tell me what the tangent slope of the solution function is there if my solution function were to go through that point. So we're just going to pick a point in the plane, and plug it into the right-hand side of your differential equation. Right-hand side of differential equation. So I'm just going to start on the x-axis here. So I'm going to start at 0, 0. And I'm going to make a little table just to be helpful. So we're going to have some xy points, and I'm going to plug them in, and I'm going to see what dy dx comes out to be. And the dy dx represents the tangent slope. So at 0, 0, our differential equation says dy dx equals 2x. So the x coordinate there is 0, so we have 2 times 0, which is 0. So at 0, 0, we've got a tangent slope of 0. So I'm just going to draw a little tangent line that has a slope of 0, which is perfectly horizontal. And then I'm going to move over to 1, 0. Now this differential equation depends only on the x value. So now I'm going to do 2 times 1, which is 2. So I need, at this point, to draw a slope of 2. And then at 2, 0, I'll have 2 times 2, which is 4. So over here, I'm going to have a tangent slope of 4, which is a really steep. And then I'm going to move left a little bit. If we do negative 1, 0, I'll have 2 times negative 1, which is negative 2. So right here, we've got negative slope. And then negative 2, 0, I'll have 2 times negative 2, which is negative 4. So right here, another negative slope, but this one is much steeper. And then notice if we were to go up or down from any of these points, the x-coordinate is going to stay the same. It's just the y-coordinate that's changing. So if we were to go from 0, 0, if we were to go up or down the y-axis, the x-coordinate would stay 0. So if we were to do like 0, 1, 0, 2, 0, negative 1, all of those points still have x-coordinates of 0, and since our differential equation just depends on x, we would still be doing 2 times 0. So all of these points on the y-axis all have a tangent slope of 0. So we're just drawing these little bitty tangent lines with slope 0, horizontal lines. And similarly, 1, 0, if we were to go up or down from 1, 0, so say 1, 1, 1, 2, 1, negative 1, 1, negative 2, all of them would still be using an x-coordinate of 1, which would result in a slope of 2. So all of these points have a slope of 2. So really, all the vertical lines that we have here on this graph have the same exact tangent slopes. Over here, they would all have slopes of negative 4. Or excuse me, positive 4. And if we go over to the left-hand side, everything with an x of negative 1 would have a slope of negative 2. Because we don't care about the y-coordinate. The y doesn't appear in our differential equation. And then slopes of negative 4. So still negative, but much steeper. So what we're creating here is a direction field. It gives us an idea of what the tangent slopes look like on our solution graph. The only thing we don't know is what particular point our graph goes through. So if I were to say that I know for certain my graph goes through the point negative 1, 2. If I know it goes through that point, we can kind of follow that point and trace the curve. Follow your tangent slopes. And it almost looks like it's going to be a parabola if we follow those tangent slopes. Looks like our solution would be a parabola. We could pick a different point and just try to follow the tangent slopes and see where they lead us. And we would probably get a different parabola that just goes through some different points. It would be located at in a different position on the graph. So we still have no idea what the solution function is, but these slope fields, these direction fields, give us an idea, at least graphically, of what the what the solution to our differential equation looks like based on tangent slopes. So let me give you another example here. So here's another example I found. This one is multiple choice. It says, which of the following is the slope field? Slope field and direction field are just synonyms. Which of the following is the slope field for the given differential equation? dy dx equals x over y. So just like we did with the last one, what I would do is I would set up a little table of values and see if that could help me figure it out. We're just going to pick some xy values on the graph and plug them into our differential equation and see what it gives us back for dy dx. So I'm just going to start with the point 1, 1. If we plug in the point 1, 1, we're going to have 1 over 1, which is 1. And as a matter of fact, because of the way that this differential equation is written, anytime the x and y coordinates match, it's going to be 1. Anytime x equals y, we're going to have 1. So the x equals y line is this line. So anytime we're on that line, we should have a slope of 1. So this first one I just drew, there are little arrows crossing that line that do not have a slope of 1. So it definitely can't be this one. So if you look at your other options, and I'm going to label these A, B, C, D, and E. Another thing that we could look at is when y equals negative x, we're going to have a slope of negative 1. So that's the line that goes through quadrant 2 and 4. And we'll have, so those are slopes of positive 1, those are slopes of negative 1. So when we are on the y equals x line, we have slopes of positive 1, just like this one does. So positive 1. And we're on y equals negative x, we have slopes of negative 1. So B matches up good so far. C does not. Here's the line y equals x, and not all of the slopes on that line have a value of 1. Here's the line y equals x, and not all the slopes on that line have a value of 1. Here's the line y equals x. All the slopes on that line have a value of 1, so that works. And y equals negative x, all the slopes on that line have a value of negative 1. So we've at least narrowed it down to either B or E. So if we look and see what those two don't have in common, what differs between them, it looks like on graph B, we've got those horizontal tangent lines on the y-axis. And we don't for E. So horizontal tangent lines, we saw those just a minute ago. We had horizontal tangent lines when the slope was 0. So if we look at our differential equation, when will x over y equal 0? X over y is going to equal 0 when x equals 0. When x equals 0, which is the y-axis. And I would plug in some numbers just to check. So as we go up the y-axis here, so maybe the point 0, 1. If I plug in 0, 1, that's going to be 0 for the x, 1 for the y. So 0 divided by 1 is 0. That's a horizontal tangent line. Whereas on this one, at 0, 1, I do not have a horizontal tangent line there. And in fact, if you look to either side, those tangent lines are nearly vertical. So now we've eliminated this one. So for these slope fields, all we're doing is we're plugging in different points in the plane, and we're plugging them into our differential equation, and we're thinking of dy dx as representing slope. And if we plug in enough points, we can get enough of these little tangent slope representations to get an idea of what our graph is going to look like.